The water looked clean. That was the problem. It sat in the puddle exactly as it always had, colorless, still, with that familiar shimmer of daylight bouncing off the surface. A soldier on the edge of dehydration might have knelt down and cupped a handful to his lips without a second thought. But somewhere above, in the recent memory of the sky, a nuclear weapon had detonated. And in the hours that followed, what fell from the clouds was not just rain. This scenario was not hypothetical. It was the defining anxiety of an entire era, the Cold War, during which military planners on both sides of the Iron Curtain ran exhaustive simulations, drafted classified manuals, and quietly tested dozens of improvised techniques to answer one fundamental question. If the bombs fell and every freshwater source was contaminated, how would a soldier stay alive? The answer they found was old. Embarrassingly old. So old, in fact, that it predated nuclear weapons entirely. And yet it worked, not just against bacteria, not just against chemical agents, but against the invisible killers that isotopes leave behind in the aftermath of nuclear fallout. It is a technique that has largely vanished from public conversation, buried under decades of technological progress and institutional amnesia. But it still works today. And understanding it might be one of the most important pieces of forgotten knowledge a person can carry. The history of soldiers and contaminated water is as long as the history of war itself. For most of human warfare, the greatest killer on the battlefield was not a bullet or a blade. It was dysentery, cholera, typhoid fever, and every catastrophe that follows when desperate men drink from rivers fouled by the dead. Ancient Roman legions understood this intuitively, digging latrines downstream and boiling water when they could. Napoleon's campaigns were devastated by typhus and waterborne illness in ways that arguably decided the outcome of wars. The American Civil War, by some estimates, saw 2 soldiers die from disease for every one who fell in combat, and contaminated water was a primary culprit. By World War I, militaries had begun to take water sanitation seriously as a tactical matter. Chlorine tablets, crude filtration devices, and rudimentary testing kits appeared in field kits across Europe. Chemical sterilization, however, came with its own setbacks. Military health reports from that era documented a persistent problem. Soldiers would receive sterilizing tablets for their canteens, find the resulting water undrinkably foul-tasting, and simply throw the tablets away, drinking dangerous raw water rather than tolerate the chemical aftertaste. The solution that eventually emerged was a dechlorinating agent, sodium thiosulfate, added after treatment to neutralize the excess chlorine and make the water palatable. It was a lesson in human nature as much as in chemistry. No survival technique, however brilliant, works if the person meant to use it refuses to cooperate. By World War II, the United States Army had developed the ERDLator, a portable field water treatment system created by the Engineer Research and Development Laboratories, capable of processing large volumes of questionable water in forward combat zones. These devices used sand filtration and chemical treatment to kill biological threats. They were a genuine breakthrough. But they were designed for a world before the atomic age. They were never built to handle what would come next. When the United States detonated the first atomic bomb over Hiroshima on August 6, 1945, and 3 days later over Nagasaki, military scientists immediately began studying a phenomenon they had not fully anticipated: the long-range contamination of water supplies through nuclear fallout. Fallout, the radioactive particles that rise into the atmosphere with a nuclear fireball and then descend over hours and days across vast geographic areas, lands on everything. It lands on rooftops, on crops, on the surface of rivers and reservoirs. It dissolves into groundwater. It concentrates in the bodies of fish, livestock, and eventually humans. The key to understanding why this matters, and why the technique that soldiers eventually developed was so effective, lies in a piece of physics that is not immediately obvious to most people. Radioactive water, in the popular imagination, is something that has been fundamentally altered at a molecular level, permanently poisoned beyond recovery. But in reality, the water molecule itself is not what becomes radioactive. What happens is far more straightforward. Radioactive atoms, primarily isotopes like cesium-137, strontium-90, and iodine-131, enter the water and mix with it as dissolved particles or as suspended microscopic debris. The water molecules remain exactly what they always were. The danger comes from what is dissolved or floating inside them. This distinction is not a technicality. It is the entire reason the technique works. When Cold War-era military researchers in the United States, the Soviet Union, and across NATO began developing survival protocols for nuclear combat scenarios, they confronted this chemistry directly. The published studies that emerged from this period, including peer-reviewed research indexed in medical and scientific literature examining ion exchange resins as tools for water purification in wartime conditions, established a scientific foundation that was quietly integrated into military field manuals and NBC, nuclear, biological, chemical, survival training programs. Ion exchange resins, zeolites, and activated carbon were identified as materials capable of physically capturing radioactive isotopes from water. Zeolite, in particular, a naturally occurring volcanic mineral that functions like a molecular cage, trapping specific ions within its crystalline lattice, proved extraordinarily effective against cesium and strontium, the two isotopes most likely to contaminate water supplies following a nuclear detonation. Activated carbon, meanwhile, demonstrated reliable performance against radioactive iodine-131. These were not exotic laboratory materials. They were cheap, widely available, and light enough to carry in a soldier's pack. But the most elegant solution, the one that required the least technology and could be executed by a lone soldier in a field with minimal equipment, was something far older than resins or carbon filters. It was distillation. And the military canteen was its instrument. Distillation is one of the oldest processes known to human civilization, with documented use stretching back to ancient Egypt and Greece, where alchemists and physicians heated seawater to capture the rising vapor. The principle is disarmingly simple. Heat a liquid until it vaporizes, collect the vapor, and let it condense back into liquid form. What remains is the water, and only the water. The impurities, the pathogens, the chemical contaminants, the dissolved salts, the heavy metals, they do not evaporate. They stay behind in the original container, concentrated and isolated from the now purified condensate. In modern nuclear science, this principle holds with remarkable effectiveness against radioactive isotopes. Cesium-137, strontium-90, and most other fallout isotopes have boiling points far above that of water. They cannot ride the steam. They are left behind. The condensed water that drips from the cooling surface is, for all practical purposes, decontaminated of the most dangerous fallout products. Soldiers in World War II already knew versions of this. Survival manuals distributed by the U.S. Army Air Forces and the British Special Operations Executive included instructions on building improvised solar stills, devices using nothing more than a hole in the ground, contaminated water, and a stretched sheet of plastic or canvas. The sun would heat the contents of the pit, the water would evaporate, condense on the underside of the plastic, and drip clean into a collection vessel below. It was a method used by downed pilots and marooned infantry units across the Pacific and North African theaters, a technique that required no chemicals, no power source, and no specialist training. It worked against salt. It worked against biological contamination. It worked against chemical agents. It would later be understood to work against fallout as well. The military canteen refinement of this technique emerged in the Cold War period as NBC warfare planning intensified. The method, as documented in survival literature and military field guides of the era, involves using a standard canteen, the military-issue aluminum or steel container that soldiers have carried since the Civil War, as a distillation vessel. Water from a potentially contaminated source is placed in the canteen, which is then heated over any available flame. A tube, a sleeve, or any improvised condenser directs the steam away from the canteen and allows it to cool and condense into a separate clean container. The steam that rises from the boiling water carries nothing radioactive with it. The fallout isotopes have been left behind in the original canteen. What collects in the receiving vessel is water stripped of its contamination. The technique requires three things: a sealed heat-resistant container, a means of redirecting steam, and a collection vessel. A standard military canteen with its cap fitted with a rubber hose, or even with a cloth sleeve wrapped around the spout to encourage condensation, satisfies all three requirements with equipment that every soldier already carried. A piece of plastic tubing. A second canteen cup. Fire. It is, in this sense, the most democratic survival technology imaginable, requiring no training beyond the basic, no specialist equipment, and no power source other than flame. What makes this story remarkable, and what gives it its peculiar weight, is how thoroughly this knowledge was validated decades later, by some of the worst nuclear disasters in human history. On April 26, 1986, reactor number 4 at the Chernobyl nuclear power plant in Ukraine exploded, releasing a massive plume of radioactive material across large portions of Europe. The immediate contamination of water supplies, rivers, reservoirs, groundwater, became an urgent crisis. Soviet engineers, racing to contain the aftermath, turned to zeolite as one of their primary tools. Tons of the mineral were deployed along contaminated waterways near the exclusion zone, functioning precisely as Cold War military researchers had predicted. The crystalline structure of zeolite captured cesium and strontium ions from the water column with high efficiency. Barriers were constructed along the Pripyat River to intercept contaminated groundwater before it could reach the Dnieper, the primary drinking water source for millions of people downstream. The technique worked. It was the same chemistry, the same mineral properties, the same principles that had been quietly written into military survival manuals a full generation before. 25 years after Chernobyl, the Fukushima Daiichi nuclear plant in Japan suffered a catastrophic meltdown following the Tohoku earthquake and tsunami on March 11, 2011. The contaminated water crisis that followed became one of the most technically demanding environmental emergencies in modern history. Hundreds of thousands of tons of radioactive water accumulated in the plant's basements and tunnels, saturated with cesium, strontium, and iodine isotopes. The water treatment systems deployed by the plant's operator, TEPCO, used zeolites as a primary decontamination tool, the same substance, functioning on the same principles, that military scientists had identified decades earlier as a field expedient survival material. The KURION and SARRY decontamination systems, large industrial units positioned at the Fukushima site, used zeolite vessels to concentrate cesium from the contaminated water with high efficiency. After the zeolite became saturated with radioactive material, the vessels were sealed and designated as nuclear waste. By the end of September 2011, just 3 months after the disaster, more than 4,000 zeolite-filled drums had accumulated at the plant, each one a testament to the mineral's capacity to absorb what no other material could so efficiently contain. The parallel is not lost on serious students of survival science. The techniques that military planners develop for individual field use, distillation, zeolite filtration, activated carbon adsorption, and ion exchange resin technology, are the same fundamental processes that nuclear engineers deploy at the largest industrial scale. The physics does not change based on the size of the vessel. A soldier with a canteen over a campfire and an engineer at a nuclear remediation plant are exploiting identical chemistry. The soldier just needs less of it. There is a profound irony embedded in the history of this knowledge. During the Cold War, nuclear civil defense programs in the United States and across Western Europe produced a remarkable body of public material on how ordinary citizens could survive a nuclear exchange. Publications like the U.S. government's Nuclear Survival Manuals, the British HMSO Civil Defense Guides, and the declassified NBC Warfare Training Handbooks included explicit guidance on water decontamination. One consistent and counterintuitive message running through these documents was a clarification that many found surprising. Fallout does not make water radioactive in a permanent or molecular sense. Fallout particles contaminate water by being dissolved or suspended within it. Remove the particles, remove the contamination. The water molecule itself is unchanged. This fact, once understood, entirely reframes the problem and the solution. Modern peer-reviewed science has only reinforced these principles with greater precision. Research published in scientific journals over the past several decades confirms that natural zeolites, particularly clinoptilolite, remove cesium from contaminated water with efficiencies exceeding 95% under standard conditions, and remove strontium with initial efficiencies between 70 and 100%. Activated carbon removes radioactive iodine with high reliability from natural water samples, a finding confirmed in studies examining the cleanup of Japanese river water following the Fukushima accident. Ion exchange resins, recommended by the U.S. Environmental Protection Agency for cesium-137 removal, have been used to clean up legacy nuclear waste from reactor sites across the country. And distillation, the oldest technique of all, removes every radioactive isotope except tritium, the one contaminant that bonds directly into the water molecule and therefore cannot be separated by steam. This is a genuine limitation, and any honest account of the technique must acknowledge it. But tritium contamination at dangerous levels is primarily a concern near active nuclear facilities. In a fallout scenario, cesium-137 and strontium-90 are the critical targets, and against those, distillation performs with reliability that modern technology has confirmed, not surpassed. Today, the principles behind this forgotten military knowledge are finding new relevance in a world that has never entirely left the shadow of nuclear risk. Emergency preparedness organizations, survivalist communities, and military training programs have quietly begun reintegrating water decontamination science into their curricula, sometimes without fully recognizing how deep the roots of that knowledge go. The U.S. Army Engineer Research and Development Center developed the Decontamination Effluent Treatment System, or DETS, a portable water treatment platform that uses sand filtration, water softening, granular activated carbon, and reverse osmosis to address contamination from nuclear, biological, and chemical agents. It is the most sophisticated expression of a principle that was first captured in field manuals, in survival courses, and in the quiet experiments of soldiers who understood that the next war might be fought not just with guns, but with invisible particles falling from the sky. What makes this knowledge genuinely valuable, beyond its historical depth and scientific elegance, is the window it opens onto how human ingenuity operates under extreme constraint. The greatest technological breakthroughs are not always the ones that require the most sophisticated equipment. Sometimes they are the ones that reveal the extraordinary potential hidden in the most ordinary tools. A canteen, a fire, a length of rubber tubing. The soldiers who trained with this technique during the Cold War prepared for a war that, fortunately, never came. But the knowledge they were given, distilled from the research of scientists, the bitter field experience of combat veterans across 2 world wars, and the hard chemistry of radiation physics, was real. It was tested not in classified laboratories, but in the most unforgiving testing grounds imaginable. The aftermath of Chernobyl, the flooded basements of Fukushima, the contaminated groundwater of sites where the Manhattan Project left its long shadow. Every time the same principles held. Every time the same chemistry delivered the same result. The canteen is not a relic. It is a classroom. And the lesson it teaches is one that every era of nuclear risk has quietly relearned, often in moments of desperate necessity, that the boundary between clean water and contaminated water is not fixed, not permanent, and not beyond the reach of a person who understands, truly understands, what radioactive contamination actually is. Not magic. Not molecular corruption. Not an irreversible sentence. Just particles. Particles that can be removed. The water looked clean. But now, with this knowledge, there is a way to make it actually be clean.